Hello, everyone, and again a warm welcome to the session of putting deep hybrid learning to work. I'm Aditya Bhattacharya, and I'm currently the lead AI/ML engineer at West Pharmaceutical Services. And yeah, we'll start with the session. But just before that, I just wanted to talk about few points about myself. So currently, I'm leading the data science and AI team at West Pharmaceutical Services. And previously I've worked in Microsoft and well seasoned in domains like machine learning, deep learning, IoT, robotics, and cloud platform development. So in the data science domain, I'm well experienced and really interested in the computer vision world. And along with that, I have worked in time series forecasting, NLP, and speech analysis. So apart from my day job, I'm actually an AI researcher at an NGO called Must Research. I'm one of the faculty members at Must Research Academy. So, to know more about me, you can definitely follow me through my website, or we can get connected over LinkedIn as well. So with this, we'll get started with the actual session topics. Maybe just one thing to mention before we actually hover over to the main topics of discussion. Since this particular session would be can be little uh, might require some in-depth knowledge of machine learning and deep learning. So I would be expecting that most of the attendees have the basic intuition about machine learning and deep learning. But if not, like no worries, feel free to shoot me a question in the chat window, and I'll try my best to answer those. But I'll prefer taking this question at the end of the session, and I'll also make sure that I finish the session well before time so that we have sufficient time left for the question answer round. Now, coming to the key topics of discussion today, I would start by introducing the framework of deep hybrid learning. Basically to know what exactly is deep hybrid learning and why do we want to go for something like a deep hybrid learning approach or an algorithm. Then I'm also going to mention about the various flavors or the various versions of deep hybrid learning and various use cases where some of these versions would be really effective and useful. And finally, I would talk about a case study in which me and my research team actually worked on a problem using deep hybrid learning. And we even compared with the conventional deep learning and the state of the art methods to see which one is actually working well. And that is where we got really good results using deep hybrid learning. So it would be a case study that would highlight the exact areas or exact use cases in which deep hybrid learning can be really effective and useful. So now coming to the main session of what exactly is deep hybrid learning. So deep hybrid learning is actually a fusion where we combine the classical or the conventional deep learning methods or the algorithms with some other type of learning algorithm. Now, when we talk about the other type of learning algorithms, right, it can be any classical machine learning algorithm, or even it can be like another deep learning algorithm with a different architecture or a different way in which the network is kind of planned and modeled. So basically, it is like converting a standard deep neural network architecture to another form by fusing another type of learning algorithm. And in throughout the session, like I'm going to also focus on the machine learning combination aspect, because that is where the main benefits of deep hybrid learning can actually be realized. And from whatever I have worked before, using the machine learning variant, I have got like really good results so far. Now, deep hybrid learning can actually have multiple forms just by the mechanism in which the fusion process happens. So if we talk about a typical deep learning architecture, right? Especially, let's take example of the image classification domain, right? Where we would have a layer of convolutional neural networks, and which would be used to do the feature extraction part. And when the features are extracted and the feature vectors are formed, then we would usually or typically have few layers of fully connected network, and after that we get the classification result, right? So if the fusion between a classical deep learning algorithm or an approach with another, let's say either a different deep learning architecture or let's say a machine learning variant happens before the feature extraction part, so that is when we call that as an early fusion mechanism, an early fusion method. But if let's say the combination or the fusion process happens after the feature extraction part. So that is where we say that we go for a late fusion approach. Okay. Um, but in order to visualize that, I would show certain deep learning architectures, and from there we are going to understand in little more depth that what exactly is a deep hybrid learning. Okay, so as I said, this is how a typical deep learning architecture would look like. Like when we have an initial let's say a set of images which can be like a radiographic images like this. So typically to get till the final prediction stage, we would have few layers of convolutional neural networks, and these layers are actually responsible for doing the feature extraction part. And once the key features are extracted and formed as feature vectors, then typically we kind of flatten it so that we get a 1D an array of feature vectors, and then we typically pass it through a few layers of fully connected networks, so that after that, like typically at the end, we normally have something like an activation function that would give us the final prediction, right? So this is how a conventional or a typical deep learning architecture looks like. Now, when we talk about a deep hybrid learning, and especially if we talk about the late fusion method, here, till the feature extraction part, it is like almost same, like it is as it is. But in the final prediction part, instead of going it through a fully connected neural network, we actually have something like a classical machine learning algorithm. It can be like, as simple as something like a k nearest neighbor or SVM, like support vector machines, or it can be like XGBoost or random forest or any other ensemble learning method, or even it can be a stack or combination of different machine learning algorithms. Okay, so this is how the typical deep hybrid learning architecture looks like when we go for a late fusion approach. And why late fusion again? Because here we see that the feature extraction is actually done by the layers of the convolutional neural network. And once the features are extracted, then we are going for when we are going for the combination approach, where we are trying to combine it with a machine learning algorithm. Now, how does the early fusion method looks like? So in the early fusion method, as I said, that the combination actually happens even before the features are extracted. So this is a classic example where we can actually use something like normally like we can use something like a 1D convolutional neural network for doing a text document classification. So from the text data, from the sequential data, we can just use something like a simple 1D convolutional neural network to get the feature vectors, and the remaining part, it remains as it is. Like we can have a series of fully connected layers and do the prediction. But in a deep hybrid learning architecture, as I said, we not only kind of go with the standard approach, but we can also combine it with other type of, let's say, a deep learning approach, where in this case we can see that we can go for something like a series of LSTM networks. So LSTM is more like a recurrent neural network which works really well with sequential data. So here, instead of having just one path for the feature extraction part, we actually have two parallel parts which are going, and these two parallel architectures or layers can actually extract different types of features. And when we have those different types of features, we can actually combine both and have one unique feature vector, and then on top of that we can have the fully connected layers to do the final prediction part. So this is a early fusion method where the combination happens even before the features are extracted. Okay, now why deep hybrid learning again, right? So let's talk about few benefits or maybe few pros and cons of conventional deep learning versus classical machine learning. Okay, so in conventional deep learning, the main benefit and the main popularity of conventional deep learning is because of the auto feature engineering part. Because in conventional deep learning, we don't have that need of doing a manual feature engineering. Whereas if we talk about a classical machine learning approach, it requires a lot of work and a lot of domain knowledge as well to do the feature engineering part. And I would always say that like it is the feature engineering work that kind of distinguishes a good model versus a better model. Okay, so In conventional machine learning, a lot of work is required for doing that manual feature engineering. Whereas if we talk about deep learning, that need of that manual feature engineering is completely removed, and that is why deep learning is quite efficient, because whenever we talk about the different filters within the deep learning model, right, it can actually extract some great features, especially for unstructured data. So for unstructured data, the different convolutional filters or kernels that we have, right, it gathers or extracts very niche features that and after the features are extracted, when we combine that with the final classification flow, it works really well. This is kind of a drawback, I would say, for machine learning algorithms, where classical machine learning algorithms actually work much better with structured data rather than unstructured data. And even if I give one of the classic examples, when I started with something like an image classification, that time deep learning was not that much popular. So that is the still the machine learning era, and we used to go with classical machine learning algorithms, something like an SVM or maybe some of the bagging or boosting algorithms, even with unstructured data like images for doing the final classification part. So that is when we used to kind of get the numerical form of the entire image, then kind of flatten it. And in certain cases, we used to go for pre-processing, but again, it requires some bit of domain knowledge. But once the features are extracted, then we used to pass it through uh, a classical machine learning algorithm. But the problem with this approach is, no matter how much tuning, machine learning algorithm is not that much efficient, especially with unstructured data. But whereas deep learning algorithms, because of that auto feature engineering, the mechanism or the benefit that we get, deep learning algorithms are much more efficient, especially with unstructured data. But there is a caveat. So when we go with some complex unstructured data formats, uh, now and if the data is limited and if it is not available in sufficient amount, deep learning models actually have a tendency to overfit on either the training data, or even sometimes it can underfit as well. So no matter how much hyperparameter tuning that we do, maybe the final model efficiency is not that good enough. Or maybe whenever we are training the particular model, we see that we are getting a very good training accuracy or any of the evaluation matrix that we use. But when we try to test the model, either on the validation data set or maybe on the testing data set, we see that the results are not that good. And that is most of the case. It is basically due to the availability of the data. So if the data is insufficient, these are some of the characteristics that we get from a deep learning algorithm. Like typically it might overfit or it might underfit. And another thing is, like, even if we have large amount of data, deep learning algorithms are slower as compared to machine learning algorithms. And machine learning algorithms actually require less computational resource than any deep learning algorithm. So that is, I would say, one benefit of machine learning algorithm. But again, it's a trade-off between the efficiency versus the computational performance. But another problem, as I said, like since sufficient data is required for a deep learning model, right? In certain domains, in certain situations, getting that large amount of data is not realistic. So the availability of large amount of unstructured data, especially in some domains, are really expensive, and it is quite a difficult process. So how exactly can we kind of combine or kind of cherry pick the benefits of these both these approaches, like a deep learning versus a machine learning approach, and fuse together to form something which is great, right? So that is where deep hybrid learning comes into picture. So deep hybrid learning, it's actually a fusion method, as I said, and which kind of combines the benefit of both the conventional approaches. So deep hybrid learning still has that auto feature extraction capability from a conventional deep learning method, because in most of the cases it actually uses something like convolutional neural network or even something like a recurrent neural network to extract the main features from the unstructured data. and it actually works really well even when less data is available. So especially in domains like let's say healthcare, or in or maybe medical data, right? So availability of, let's say, labeled medical data in most of the cases, it's very difficult. Although there are approaches or there are different techniques which can kind of can be a workaround for those problems. But ideally, like if we have a technique or an algorithm that can work well with even less data, then like nothing like that. And at the same time, a typical deep hybrid learning algorithm, and especially if we talk about the machine learning variant, right, it is much faster, more efficient, and less computationally expensive than a classical or a conventional deep learning algorithm. Now, at the same time, deep hybrid learning actually works much better than some of the advanced methods like transfer learning. So you may kind of debate, and we can say that, let's say, in some cases, the main idea of having a transfer learning itself is to work with less amount of data, where we kind of train our model with large amount of data, and then when we have the pre-trained model, we just use the weights of the pre-trained model, and then using those weights, we try to fine tune the algorithm or the model on our set of data to get a much accurate results. But like if I go over to the case study part as well, right, it will again kind of highlight and re-emphasize that transfer learning also fails in some cases, especially when the distribution of the data which is used for training the initial model or the pre-trained model is completely different from the data that we are using. So say for example, if I'm using my model on a on a radiographic, let's say, images, but let's say my data is, or my model is trained on something like an ImageNet database, right, which is normally taken from the different normal images we have, like normal camera images. So it is quite different from the radiographic or MRI images, right? So in such cases, transfer learning may not work well. And even with the research work that me and my team has done, we actually kind of uh, got such results which prove that transfer learning completely failed, whereas deep hybrid learning actually worked really well in that case. So deep hybrid learning is actually most better than even the individual deep learning or even classical machine learning approaches. And as I said, it tries to combine the benefits of the traditional methods and gives us something which is really good and which can actually match the human level performance. Now let's talk about some flavors or different versions of deep hybrid learning. Uh, Initially we talked about two main approaches of having a deep hybrid learner, one by the late fusion technique and the other by the early fusion technique. But now, like, let's talk about the other variants as well. So for example, can have a machine learning variant where in maximum cases the feature extraction is done by a deep learning algorithm, and once the features are there, then we can do the classification part by a classical machine learning algorithm, like a classical machine learning learner. So this is the late fusion technique that we talked about, and it is actually the most I felt this is the most beneficial variant. But there are other variants as well that works quite good also in some cases. uh, in the early fusion method, there are certain cases where people go for combining a deep learner for feature extraction, and at the same time, people use something like a machine learning algorithm, not just for the classification part, but at the same time, people go for clustering algorithms and cluster the raw data. And once the cluster labels are obtained, right? So those cluster labels are also combined with the features that are extracted from the deep learner as additional features. So in such cases, it is a combination of both a deep learning algorithm and a machine learning algorithm, which is used for the feature extraction. And once the combined features are obtained, then it can be passed through any machine learning learner or a deep learning learner for the final, let's say, the classification work. So that is one variant or one type of variant where we have machine learning algorithms and at the same time deep learning algorithms, and we are using this as a early fusion method. Now let's talk about the deep learning variant. So in deep learning, encoder decoder method has been quite popular for really quite some time, and that can be a good example of a late fusion deep learning variant, deep hybrid learner algorithm actually. So here an encoder deep learning algorithm can be used for doing the initial feature extraction part. So when we talk about the initial feature extraction part, right, an encoder model can actually be used to obtain, let's say, the latent space vector. So a latent space is nothing but the most simplified form of the data, using which the entire data can be again reconstructed. And so let's say when the initial features are extracted using an encoder model, then that set of features can actually be passed through a conventional deep learning algorithm, and like for the final classification. So it is like clubbing together two different types of approaches, two different types of deep learning algorithm. And since the combination part happens after the initial feature extraction, we again call this as a late fusion technique. Similarly, for early fusion, and especially the text document classification example that we saw, right? That is an example of an early fusion deep learning variant, where two different types of deep learning algorithms are used for the feature extraction part. And once the features are extracted, we just combine the features together to form one feature vector array, and then pass it through a fully connected layer of for the final classification. So these are the, on a very high level, these are the four different types of variants that we can normally have. And all of these variants are actually useful for specific purposes. But the one that I saw like most benefit so far is with the machine learning variant with the late fusion technique. Okay. Yeah, so moving on, let's talk about the case study that kind of highlights the main benefits of deep hybrid learning. So we kind of called this framework as NUMODRIL, which is kind of a nuclear morphology optimized deep hybrid learning. Now let's maybe talk about the problem statement first. So the main problem statement is about automated detection of ovarian cancer cells from nuclear morphology images. So nuclear morphology images are actually something which looks like this, the image over here. But at the same time, since it is a quite a critical use case, right? We want to come up with a model that can predict with the highest possible accuracy and speed. But the challenge here was the data set which we had was highly imbalanced. And at the same time, the data set was very small. So if we can see over here, right, the data set just had like 314 images, out of which 262 of them belong to the cancer samples. And there were just 52 images that belong to the non-cancer samples. So it's like the majority of the class had almost 84% of the data, whereas just the remaining 16% belong to the minority class. So in such a situation, if we actually go with any normal classical machine learning or deep learning approach, it is highly possible that the algorithm would be biased towards the majority class, because majority of the data is actually uh, 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 kind of adds that bias or the tendency to predict the same majority class every time we kind of try to do that. So we would need to come up with a way how to handle the imbalanced class problem. But just to kind of give a bit of a more context, the ovarian cancer cells were actually easily distinguishable because of their large nuclear morphology size, and at the same time, the cells that we see over here, not only the size of the cells were larger, but at the same time, the density of the cells were much higher. So from a if we compared the same using a human level performance, a human being, or we actually did this experiment also, like we ask a group of experts to do the same manual prediction part, and roughly we found that on average almost 92% of the data were rightly predicted by the human group of experts. So that was our so basically the Bayesian error was 8% for us, or for the team to have. So basically, we would need to come up with an algorithm or a model that is like at least like 92% accurate. Otherwise, like there is no point in coming up with something which might not even beat the human level performance, right? So for this method, like we actually experimented with a number of state of the art deep learning architecture, and at the same time we experimented this with deep hybrid learning, and we found that the deep hybrid learners were actually much better than the conventional methods, and even things like transfer learning failed in such cases. So let me maybe initially talk about some of the data pre-processing that has been done, because like even if deep learning algorithms are known to do the auto feature extraction part, right? But if we kind of use the domain knowledge that we had, and use something like a classical computer vision algorithm to kind of uh, make those images more prominent, that gives us a better chance, especially for the deep learning models, to extract better features and get much better results, right? So that is where we have this kind of a data pre-processing pipeline, where we used morphological masks to kind of mask the most prominent and the larger cells over here, and at the same time we had to kind of sharpen the image to make it more prominent, and we can clearly see that the sharpened image is much more visible. And at the same time we kind of darkened the background, so that like to basically to remove noise as much as possible. And finally we had a grayscaling mechanism so as to reduce the number of channels in the image, and basically make the algorithm much more efficient by doing lesser number of computation. Now that was about the pre-processing part, but the major challenge we had was not only that the data set we had was small, but it was imbalanced. So we had to come up with a way to kind of fight the data imbalance problem. So data augmentation is one of the popular approaches which people normally take, but when we went for just for data augmentation, the results that we got was not that good. So that is when we tried to go for other approaches, like let's say a weighted classification, or something like a downsampling technique. So those things actually did not work that well, and that is when we use something like a SMOT, which is called a synthetic minority oversampling technique, which used for the upsampling the minority classes, right? That worked really well for us. Now, one big benefit that SMOT gives is it kind of generates synthetic samples of the minority class images, let's say in this case. But at the same time, it makes sure that the generated images are statistically different, or statistically it has some variance from the actual class, and but it makes sure that the overall properties are kind of preserved. So what it actually does is, in this way it kind of does not add any additional bias to the minority classes. Otherwise, if we just simply, let's say, copy paste the minority class into, let's say, multiple version, and then we say that okay, our data set is balanced now, but that is one approach that actually does not work that well. The main reason is like it kind of adds that additional bias to the data, and the final model does not perform that well. Okay, so that is why like we went for SMOT. And SMOT is quite popular, by the way, like especially for with structured data, but we tried with unstructured data and the results were actually quite good, and it did help us to solve the imbalance class classification problem. Now let's talk about the deep hybrid learning architecture that we used. So it is similar to the the previously seen late fusion machine learning variant that we talked about. So initially, whenever we had that input sample, we passed it through layers of image pre-processing pipeline, and once we got the pre-processed image, then we had a few layers of convolutional neural networks, or deep convolutional neural networks, to do the feature extraction part. And once we had the extracted features, we just passed it through a machine learning algorithm like random boost and XGBoost, random forest and XGBoost, and it gave us really good results. Now, one good thing about this architecture was it looks quite simple, but it is actually a 21 layers network. And the best part was the custom incept and the squeeze layers that we had, and it looks kind of similar like a nested convolutional neural network, and which helps us to gather very good features from the data. And this particular approach or network was actually inspired by the inception layer architecture that we have, where in inception network also, like, we have a similar set of nested convolutional layers which can actually extract very good features from the raw data. So this was about the architecture, and as I said, we went for the late fusion approach with the machine learning variant. And not only that, the results that we got were better, but at the same time, it was much faster. Now, in the model results, right, here we can clearly see that with the training and the validation learning curves, there is no presence of overfitting. So the fitting was really good, and we actually used something like an AUC ROC score as a metric. And the major reason is, if we had used something like an accuracy as a metric, right, and since our initial data was imbalanced, then it is highly possible that if the model predicts everything as the majority class, then our accuracy would be high, but actually the model is not that great. So that is where going for something like an ROC AOC score is much better. And even if we see the loss curves, we can clearly see that there is no presence of significant overfitting and not even underfitting. Like, it is actually showing a very good fit that we got using the deep hybrid learner model. And similarly, if we see the confusion matrix results, right, like over the training set, validation set, and the test set, the results are quite promising and much better than the human level accuracy that we initially thought about. Like, that was our benchmark target. Now, as I said, like, we experimented with multiple approaches and multiple algorithms. So these are some of the model comparison results that we see. The best results are actually obtained using the random forest and the XGBoost variant with the deep hybrid learner. And the results are like almost similar. It's quite good. It was quite fast. In terms of speed, XGBoost was little faster than the random forest one, but like it's almost same. Like, it was not, it was not a statistically significant difference. Now, when we actually used a conventional deep learning model and trained it from scratch without using any kind of transfer learning involved in it, we did get good results. It's not bad, but it is not as good as the deep hybrid learning approaches that we got. The training accuracy was very good, but we see that like the validation and the testing scores were a little lower, which shows the presence of overfitting. And as I said, deep learning approaches is actually like quite prone to overfitting sometimes, and we can also see that. Now, when we see the transfer learning approaches, we can see that even if we go for something like a dense net architecture, which has like almost 201 layers, whereas the deep hybrid learning algorithm had actually 21 layers. So even if going for a complicated architecture with transfer learning, the scores that we were getting was actually very low. So even the training score was not that good, and even the validation and the testing scores were much lesser, which clearly shows the presence of overfitting. And if we go with some other architectures with transfer learning, so we went with ResNet 50, which has like 50 layers, and even we went for InceptionNet with transfer learning, and even VGG16 with transfer learning. The results were not at all good and maybe not comparable with the results that we got with deep hybrid learning. So this again kind of shows or proves us that if the data that we are using, uh, you know, for our final classification part is different in terms of distributions or dimensions than what is used for the initial pre-training part, then transfer learning might not work well. So transfer learning can also bring a lot of overfitting and even underfitting sometimes. And this is one classic example where deep hybrid learning was actually quite efficient, and the results like clearly speaks for itself. And kind of we can see that whenever we have a limited data set, and even if it is unbalanced, right, we saw a few techniques or methods to kind of balance it out. Now let me quickly do a code walkthrough. I think that would be helpful. So and again, like, these codes are available in the GitHub link that I shared. So feel free to take the code. But the data, like, I won't be able to share that. But feel free to use with your own data and use the same approach. And in case if you see any changes from what we saw over here, feel free to let me know. We can discuss on that. But typically, like this is how the initial pre-processing pipeline looked like. We used morphological filters to create the mask and applied the on top of the original images and kind of sharpened the image, and then we had the grayscale version of it, right? So typically this is how it looks like. And once the initial pre-processing part is done, let me maybe show about the smart part. So I hope my screen is visible as well, right? Okay. So this is how the smart part is done. So whenever we have the the imbalanced data set, which we can clearly see, like we had almost 196 images belonging to class 1 for the training set and only 39 for class 0 for the training set. Then we applied smart and it kind of balanced everything out. So it kind of upsampled or oversampled the minority classes. And just maybe one point to add or clarify over here, uh, always try to use something like a smart or any of the upsampling techniques, mostly on the training set. But when we saw the image pre-processing pipeline, right? So that has to be applied in all the sets, like training set, validation set, and test set. But something like smart should only be applied at training set, so that we are not bringing any other additional bias to the data. Okay. Now, next we will see the model architecture briefly. And again, I'm not going into much details, but kind of giving the initial intuition so that like if anyone wants to try the code out on themselves, like it would be much easier to understand. So typically this is how the deep hybrid learning architecture looks like. As I said that we had the, the custom incept and the squeeze layers, right? And it is just a combination of the incept and the squeeze layers. And which kind of looks like this. So totally this particular model had around 21 layers, and even like it can finally have the fully connected dense layers with the typical activation function, right? And this is the same architecture that we used for the convolutional deep hybrid learning model. But uh, when we talk about combining with the classical machine learning approach, right? So this is how it is typically done. So basically, whenever we have the model trained, right, we can just cut out the bottom layers of the model and then use that for extracting the model features. And once we have the model features, we can just define a classical machine learning algorithm like this and just fit the features along with the training labels that we had, and based on that we can actually get pretty good results that we even saw in that particular table. So this particular notebook has examples of trying with XGBoost, SVM, and I think we should have random forest as well. And so these are some of the typical machine learning algorithms that we tried with. But at the same time, if someone wants to try with something like a stacked model or maybe something like a combination model of different algorithms, even that works really well. Okay. So going back to the presentation. Yeah, so that's like mostly it. And we saw that from even from the case study results that, deep hybrid learning is quite effective, especially in cases where transfer learning did not work well. So just to summarize what we discussed so far, we kind of learned what exactly is deep hybrid learning and what are the typical benefits that deep hybrid learning provides. At the same time, we saw different types of deep hybrid learner, like different variants of it, and mostly kind of tried to focus on the late fusion approach with the machine learning variant, because that is one approach which is quite fast. At the same time, the results are good, and that works with well with limited amount of data, especially if the data variant or the distribution is completely different from usual set of images. But if the data is little complex and we need to learn complex relations from the data, we can go with other variants of deep hybrid learner, which can give really good results. Okay, so that's mostly about it. So that's all from my side. And in case if anyone has any question, right, we can definitely open the floor for Q&A. And at the same time, if we are not able to cover like some questions, then definitely feel free to drop me an email, or maybe let's connect in LinkedIn and we can discuss further.